Dinesh Gaitonde is a senior fellow in the FPGA architecture group at AMD. So prior to his role as an architect, he was a member of the team that defined and built Vivado. He has worked on several companies prior to AMD/Xilinx, primarily in the role of an EDA researcher. He holds a PhD in ECE from CMU. His research interests include reconfigurable computing architectures, applications that map onto them, and design automation on such architectures. So thank you so much for coming, and take it away.
Thank you. Thank you, Mohammed, for inviting me. So I'll be talking about our latest generation of FPGAs. We don't even call it FPGAs anymore, and I'll explain why as I go through this presentation. Our next generation of adaptive SoC architecture. So what I will talk about are some of the reasons for the decisions that we took in our latest generation architectures, and technology reasons, market reasons, other reasons, and hopefully it will be instructive of how we in the FPGA world navigate technology constraints and market pressures. Okay. So I think this should be not new for anyone who's worked in this field. CPUs and GPUs offer a tremendous amount of flexibility in terms of software programmability. They are not necessarily hardware adaptable. They have a fair amount of workload flexibility, but they suffer a lot in when it comes to optimizing for latency, optimizing for power efficiency, and so on. Right, and that's on one side, and custom ASICs are on the other side. What we wanted to do in this generation was to have a balance between the pros offered by CPUs and GPUs and those of custom ASIC, and do that in a situation where the complexity and development time of a workload being mapped on such an architecture goes from months, which was typical for previous generation FPGAs, to something like weeks. Right. So that was the main idea when we started architecting this Versal family. So let me just give you guys a rough idea about what a Versal device now looks like. This is of course not to scale. It is not to it's not even representing the physical architecture of the device, but how we think about the device now when we think about Versal. Traditionally, on an FPGA, the only thing you would worry about is what is colored here as programmable logic. Right? In Versal, we do not just build an FPGA anymore. There are a bunch of other SoC components that are an integral part of Versal family, and I'll talk about these in some detail now later on. These components may or may not be present in every Versal FPGA, in every Versal SoC, but we have architected it so that different accelerators, different domain-specific blocks can be plugged into this platform relatively easily. And in fact, the wide variety of devices that we have announced in this family is testament to that, to the ability to integrate various SoC components relatively seamlessly. So let's talk about some of the pressures that we were noticing when we started architecting Versal. It should be no surprise to anyone who's worked in this field that it's becoming increasingly difficult to rely on Moore's law for scaling. Technology, performance, and power scaling continues to be challenged, and this is not unique to FPGA. Traditional scalar processor performance and even multi-core performance is been stagnating. One aspect of performance scaling that is traditionally not thought about in more detail, but is key for FPGA is interconnect scaling. Interconnect scaling is even more severely challenged than transistor scaling. People, when people announce new technologies, they focus on transistor performance, but interconnect scaling is a larger determinant of FPGA performance, of reconfigurable computing performance than even transistor scaling. Secondly, there were unique market pressures. Compute intensity demands from the markets that we were trying to service are skyrocketing. And we have to live under now strict power budgets. The amount of performance you can bring to the table is now more and more constrained by the power envelope that you are operating under, more than even more than technology. What used to be true a couple of generations ago was, as long as you have a power supply that you can plug your card into, you wouldn't worry about power as much. You would worry about peak power because you have to design your card so that it is able to supply that peak power, but you would not worry so much about operating power. Now that when we are living under like data center markets, average power consumption is a large part of operating expense, and so we have to manage to live under those power budgets and still deliver performance. And finally, FPGAs are deployed in lot more real-time applications which have very strict latency requirements as well. And finally, as I said, we want to improve designer productivity, and designers do not want to understand the details about an FPGA. They are experts on their domains. It might be an HPC domain, it might be 5G, it might be some industrial automation and so on. They are not necessarily Verilog experts. They are not experts at squeezing the last megahertz of frequency from an FPGA. And we wanted to make this device attractive for programmers who are operating in their domain. Just like, for example, a GPU or a CPU programmer doesn't really worry about the microarchitecture of the CPU necessarily when they're developing an application for that. So this, again, is our Versal device now. So let's look at a few of these key features of this device. Besides the core FPGA, we now have a processor and platform management as part of every FPGA. Versal is the first device where a processor is an integral part of every Versal device. You won't have a Versal device without a processor. There are hardened memory controllers, which is again new for AMD FPGAs. Another key new thing that I'll talk about a little bit is device pervasive NoC. Every Versal FPGA now comes with a network on chip, and I'll talk a fair bit about this, unlike previous architectures. And there is an option to have dedicated accelerators attached to this NoC. We have already announced accelerators for real-time signal processing, for AI ML workloads, and there are things in the pipeline for a bunch of other applications as well. And covered on either side by gigabit transceivers for connectivity. So let's talk about how we try to scale various things about our platform. So let's first talk about interconnect scaling. We'll talk about fabric interconnect scaling first. So why do we have to worry about interconnect scaling? Technology scaling would not give us performance if we simply designed how we traditionally designed an FPGA. So here, what I'm showing in this graph is a typical resource on an FPGA. So let's start with at 40 nanometers. I have a resource which has some logical distance. It wants to go some number of logical units away to deliver some amount of connectivity. Right? as I go to finer and finer geometries, the logical distance decreases. So you would expect the performance to improve. But the metal resistance and capacitance is increasing at such a large scale that if we simply scaled with technology, I would see worse performance at 7 nanometers than even at 40 nanometers. So I cannot scale my interconnect at the rate at which, on paper, the fabrication technology permits me to scale because of the nature of FPGA. I have to manage interconnect scaling as a first-class problem in order to be able to deliver performance and routability for the devices that we are building. And we have two rough ideas to do it. One is to increase the supply. Increase the supply in several ways. One way would be to actually have more metal layers on your stack in order to increase the supply of metal. And the other way is to be more efficient in how we are using interconnect. And that is network on chip, and we'll talk about that later on. And second is to decrease the demand. The same design, when implemented on Versal, should demand less interconnect than when implemented on traditional, on previous generation FPGA. So coupled with both of these, we think we have a pretty good solution for interconnect scaling. So let's talk about this. So even though metal is not scaling, as long as you guarantee that the span of the metal is not a whole lot, metal is scaling reasonably well. So in order to exploit that, what we did in Versal was to coarsen our logical block. Our logical unit is a CLE, and so in Versal, we coarsened that CLE to 4x the CLE of our previous generation, so that communication between these CLEs now does not require me to go to a general purpose interconnect. So we had one more level of interconnect hierarchy within a CLE. So as long as you promise to stay within a CLE, you are not putting no stress on the general interconnect. As you can see, what we are able to do because of that is, in previous generation architecture, about 6% of the connectivity could be contained within one CLE. And out of that 6%, not out of that 6%, but even though 6% of the connectivity was contained within that CLE, because of the artifacts of how we design our routing architecture, only about 2% of the connectivity was satisfied without stressing the general interconnect. But in Versal, close to 18–19%, about a fifth of all connections are now contained within the core CLE. And 15% of all connections now do not need to go to general interconnect at all. So this results in a significantly less stress on general interconnect than what previous generations had to do, thereby helping with interconnect scaling. What we do at AMD for quite a few generations now is not to build a device with just one piece of silicon, but to arrange different pieces of silicons on an interposer in order to deliver much larger capacity devices than would be economically feasible if we insisted on a single device. Okay? And we've been doing this for a few generations. We've had huge capacity FPGAs for the last 3 or 4 generations now. And in fact, I want to just plug, we just had an announcement recently of a device which is even 2x larger than our largest device announced so far using a similar technology. Right? So what we did for when we build devices with different pieces of silicon was to recognize that connectivity between these different devices traditionally was concentrated in channels. So what would happen is, if this is one piece of, I'm assuming you guys can, let me just see if I can create a laser pointer here. Assume this is one piece of silicon, assume this is another piece of silicon. Traditionally, we would have connectivity come in chunks. So I would have connectivity between these two pieces of silicon in one area. Then there would be a long piece of physical area where there would be no connectivity, and the connectivity would be bunched in essentially islands. In Versal, we decided to have connectivity be ubiquitous. So connectivity is now done not in islands, but it is distributed throughout the device. And as you can see, when I distribute this throughout the device, the demand for connectivity, the demand for this reduces as I increase the amount of distributivity in my connectivity, right? So the interconnect demand reduces. Secondly, on the interposer, we realized that most of the metal in the interposer was used for connectivity between two SLRs, between two dies. And so a lot of interposer tracks were free in order to permit us connectivity between the same devices, between the same dies, as long as they are on an interposer. So we give more supply of metal for large devices, because large devices are on interposer, and now interposer gives me the capability of having even more tracks for each device. So both the amount of interconnect supplied and the amount of interconnect demanded was optimized for in this generation. Let's talk about another vector along which we tried to scale interconnect, and that's network on chip. In fact, some of the earliest academic work on network on chip was done by your professor, Professor Abdul Fattah, and Versal is the first commercial product to embody that innovation. So why do we need a hardened network on chip? Lot of the systems that are now implemented on FPGAs require very efficient data movement. Large amount of data is being shuffled all over the chip. For example, one key example of that is our memory standards. The amount of bandwidth required that is supplied by memories now doubles almost every generation. Not to mention newer memory styles like HBM, which are even higher bandwidth than DDR. It is impossible to consume all of this memory very close and be also close to the memory, because the amount of memory bandwidth is so much that you would not have space close to the memory in order to consume that memory and compute on it. So this memory can only be consumed at geographically distant locations compared to where the memory is situated. And so that data transfer needs to be offloaded from general interconnect, because that data transfer will have to be done by almost all customers. And so because we have need for systematic data transfer, structured data transfer across the entire device, hardening it makes sense. And so this generation, we hardened a network on chip, and this is now an integral part of all Versal devices. Every Versal device has a network on chip, and all resources attached to this network on chip appear under a unified memory space. So you can have hardened clients or servers attached to the NoC. You can have fabric clients and fabric servers attached to the NoC, all living under a unified memory space. So the programming model becomes far simpler. The network on chip that we have on our Versal devices is quite a bit different from the network on chip that people are familiar with on traditional ASICs or SoC. The first in this is that when we design an FPGA, we are designing a family of FPGAs. We don't design one device, which means when we architect the network on chip, we have to architect in such a manner so that we can scale the NoC in various ways. We can scale the NoC as memory bandwidth increases. We can scale the NoC as the device capacity increases. As a result of which, the NoC topology cannot be fixed. It has to scale with the device size. We also do not know the traffic routes that the NoC is going to operate under, because after all, this is a programmable chip. The customer decides what traffics they are going to impose on this, which requires us to have a lot more programmability in each switch and in each link than what is required of a traditional network on chip. I won't go through the rest of the details, but essentially a lot more programmability has to be put into the switch than what a traditional SoC NoC requires. Right? And in fact, this is actually a very good research problem, because this is now becoming integral part of FPGAs, figuring out what kind of flexibility needs to be there in the components that make up a network on chip. Is a problem that is similar to the well-studied problem of traditional FPGA interconnect, where people studied what kind of switches, traditional FPGA switches are efficient. And so similar problem now arises on network on chip. Right? What kind of switches, what kind of programmability needs to be offered in a switch in order to make it both efficient and powerful for FPGA traffics. So the NoC components that we have are straightforward. There is a NMU, which is a master unit. There is a high-speed transport, and then ends with an NSU, which is a slave unit. The data is transferred as packetized over the high-speed transport network. There are some NoC topology highlights. We have 4 NoC lanes attached to memory controllers, and the reason why we have 4 NoC lanes is because we want to give flexibility to any programmable logic master to communicate with any any memory controller. So we don't want it to be the case that this fabric only talks with this memory controller. We want it to give a lot of flexibility here, because we want to operate under a unified memory controller space. We have 2 physical lanes per memory, roughly per memory controller. We have 2 vertical physical lanes. Sorry, is there a question? Okay. There are 2 physical lanes, each operating at a gigahertz, delivering 32 gigabytes per second in each direction. Okay. So the way we think about this device is, as we build wider and wider devices, the number of memory controllers keep increasing. And so the number of vertical channels keep increasing as we build wider and wider device. So the cross-sectional bandwidth scales with the memory bandwidth. Vertically, the memory bandwidth is not scaling, but the number of people who demand memory bandwidth increases. So the memory bandwidth is not scaling, but the number of claimants on that memory bandwidth increases. And so the number of ports that we supply increases when we scale vertically. So horizontally, we increase the amount of memory bandwidth we support. Vertically, we increase the number of ports we support. This entire connectivity scales seamlessly across dies. So if you are on some different die and you want to access memory on a different die, it's still a unified memory space. So what are the advantages of hard NoC? Right? So the traditional FPGA routing has the same semantics as that of a metal wire in ASIC. So when you are designing an ASIC, you define a wire, and that wire has the same semantics as an FPGA wire. Of course, an FPGA wire is much more complicated because it has to go through routing muxes and so on, but the semantics are the same. Whoever claims that wire has control of that resource for all time. Driver may send data, may not send data in every clock cycle, but doesn't matter whether the driver sends the data or not. The driver owns that metal wire, and all loads that consume that data see that data in one clock cycle. Right? In NoC, we do not have that. We do not have that claim. So if a particular resource is not being used by some claimant at a given clock cycle, some other claimant can use the same resource, which means the resource utilization improves. It becomes a more efficient way to route data compared to FPGA, because we need fewer physical wires to effect the same data transfer. So it's a much more effective interconnect utilization. What we give up, though, is that we give up any claim that data will arrive at a particular time. So determinism is what we give up. More and more, we are finding that communication in FPGAs is now structured, which means, like, for example, for Ethernet traffic, the fact that that Ethernet traffic is processed in one clock cycle is not important. So structured traffic, we can live with non-determinism flight times. And that's the thing that we exploit when we use NoC to do interconnect transfer, to use data transfer. Okay. So that's about how we scaled interconnect. Let's talk about how we scaled the compute. Let's talk about how we scaled the compute in Fabric. So one of the things that we did in Versal is to add a collection of registers for every input of every block. What these registers help us do is they help us pipeline a design more aggressively than what was possible. And that, coupled with an ability to delay the clock arrival for these registers, means that these registers can appear as if they were placed in the middle of interconnect. That gives us a much better ability to pipeline more aggressively, as the next slide shows. So for example, let's suppose we have this design as shown above. You have about 1.8 nanoseconds period on the left-hand side, about a 1.3 nanoseconds period on the right-hand side, just 1.8 nanoseconds period on the device, on the path on the left, and a 1.3 nanosecond period on the path on the left. Right. What we now do is we retime this register. So we retime this register by moving it through the CLB on the inputs. Why are we able to retime it? Because now all inputs have registers, so we are able to do that. So when we do that, we are not saving a whole lot. We are just improving the period by about 200 picoseconds. So we get to about 1.6 nanosecond period, right? Now we can pipeline as well, because now we, instead of simply retiming, we could have pipelined at every CLB input. Now when we pipeline at every CLB input, it appears also as if we have not saved a whole lot, because this 1.5 nanosecond period is still there. So we went from 1.8 to 1.5. But because we can now delay the clock on this guy, even though physically it is placed here, in time it appears as if it's in the middle of the interconnect. So because of this feature, we are now able to get a much better performance on the device than we would without having this feature. So without spending a lot of area to physically provide for registers in the middle of the interconnect, by just providing registers at the input of logic blocks, we are able to essentially give the same functionality. So this lets us pipeline very aggressively. Another key thing we did in Versal for performance is improve on the clocking. As device performances increase and as the device size that we are building grows up, clock skew becomes clock skew takes an increasingly larger chunk of your period. So we had to bring that under control in some sense. So there were two things essentially that we did. The first thing we did was we realized that a lot of the time users require one clock and then a divide by 2, a divide by 4, a divide by 8 clock. And usually in FPGAs, the way people used to do it was they had to generate a 1x clock, and then they would generate a half clock, and they would generate a fourth clock, and route all of these to various places. And because they would have to route all of this in various places, the amount of accumulated skew between them would be tremendous. What we did in Versal was to have local clock dividers, programmable clock dividers throughout the FPGA. So instead of routing now 3 different clocks, you just need to route 1 clock, and then depending on what you need, you can either divide it by 2, divide it by 4, just at the very end, which means the bulk of the clock distribution skew is not seen when between a 1x clock and a 2x clock. Secondly, what we've done in Versal is to have adaptive deskew. Every region in the FPGA registers what was the arrival time of the clock there, negotiates with its neighbors what was the arrival time that neighbors saw, and then adjusts its delay so that all the arrival times are within a narrow region. So as soon as the device boots up, it does this, which means the spread that we have in clock arrival times narrows quite significantly as a result. Right? This also helps us reduce skew. And finally, there were some circuit tricks in terms of ensuring that the clock supply is robust, ensuring that the metal that was used for clocking is robust, and so on, which further reduces the jitter that we see in global clocking. Right? So this is another way in which we permit higher frequency design implementations on Versal. The big hammer, though, for compute scaling was AI engines that we introduced in Versal. So let me talk about AI engines a little bit. So AI engines is our first attempt at having a heterogeneous architecture where coarse-grained reconfigurable arrays are coexist with traditional programmable fabric. The coarse-grained reconfigurable array is domain-specific. In this case, the domains that we were targeting early on were, real-time signal processing for 5G and ML. So what we have now is a much more coarser tile than a compute tile in FPGA. It's a much more coarser tile, much coarser than a CLE, much coarser than even a DSP. It is actually a block with its own ISA, in instruction set architecture. So the way it is structured is you have a coarse-grained array. That coarse-grained array can talk to PL. And in fact, I don't have an arrow. It can talk to memory directly, or it can talk to processor. So it can coordinate its execution with all the other key components of a device. There is a processor, there is a local scratch pad memory that it can use, and then there is an interconnect which helps it communicate with neighbors, and there is dedicated cascade connectivity with immediate neighbors on all 4 sides. So you can have data transfers, you can have multiple types of data transfers in this coarse-grained array. I'll get to that in the next slide. Right? What this permits you is you can now orchestrate the entire AI array to implement a workload with deterministic performance and low latency. Right? Unlike a GPU architecture or a CPU architecture where you have no guarantees on latency, because these work in an orchestrated manner, you have deterministic performance and you have low latency. Right? I won't go into the details of well, I have some time, so we can talk about that. Right? So what are the units that make up the AI engine? We have a scalar unit, 32-bit RISC processor essentially, and a vector unit, a 512-bit SIMD data path there. We have a memory interface and a stream interface, and a bunch of load store units. What this permits us to do is it has characteristics of a VLIW architecture because we're able to do a lot of operations per clock cycle. 2 vector loads, 1 multiply, 1 store, 2 scalar ops, and stream access all in 1 clock cycle. Right? And because it supports SIMD vector lanes, we are able to do vector operations on various data types: 8-bit, 16, 32 bits, even single precision floating point. The first generation of our AI engine could do about 128 max per clock cycle on intake. It's just one tile. Right? Over the last few years, we have now had variants of this AI tile. We have tiles which are now focused just on real-time signal processing, and we have another tile where we have defeatured all the signal processing. We have enhanced the AI/ML capabilities, and so the same general architecture can support a device that is focused on beamforming, on signal processing required for 5G, and the same architecture with a different coarse grain array can support ML applications. Right? And as you can see, the AI tile that supports ML applications is quite a bit different from the AI tile that is more general purpose, that supports also real-time signal processing. Right? So in ML applications, you want a lot of local memory. You want sparsity support. You want diverse data types. You are not necessarily interested in, say, complex arithmetic. So we can now tune the AI array. We shouldn't even be calling it an AI array. I can tune the coarse grain array to specific demands of the applications. What kind of data movement can we do on this AI array? There is a simple pipeline. Some AI core computes and ping pongs between B0 and B1, and the next AI core also ping pongs takes its inputs from either B0 and B1 and dumps it to B2 and B3, and so the entire pipeline can execute smoothly. Right? We can have a broadcast. An AI core can broadcast its data to multiple streams, which can then compute and then merge. This is also supported by the AI programming model. You can have streaming communication, and the streaming communication could be not with neighbors, because there is an entire interconnect on the AI array. So you can dump your data to the memory bank right next to your core, and that can then be read by a distant AI core, and it doesn't have to be neighbor communication. You can do a streaming multicast. You can have a streaming operation, which is multicast as well. So for example, if you want to stream activations which multiple cores want to operate on, you can do it as well. So the compiler figures out what is the right kind of data movement architecture required for a particular workload. Right? And of course, you can finally, if you are if the compute is right next to you, you can simply stream using Cascade, which has very good performance, but much less flexibility, unlike the non-neighbor streaming, for example. Right? So in short, we have such an architecture now. We have AI array, then there is some kind of shim, essentially, which helps helps the AI engine communicate with rest of the blocks that make up the device. And so what we are able to do now is AI engine can use the PL directly. So for example, it can use PL to augment memory. So for example, it can use the memory in the PL as augmented memory for AI engine. It could use the connectivity in the PL to have special connectivity. So for example, if it wants this AI to communicate with this AI, it can use the PL to do that communication. It can also use the PL to augment the instruction set. So for example, if it turns out that the AI core does not support a particular instruction that some end application has figured out is really important, you could implement that in PL and use this connectivity and then use PL as part of your AI compute. Okay? That's possible now. You can also communicate directly to the processor from the AI and the platform management controller. So the processor could initiate some AI workloads on its own and then take the results of it. So for example, if you want to map a processor AI workload on this, completely ignoring the PL, you are able to do it. So you can accelerate ML workloads without the function, without PL being part of it at all. And finally, AI is able to, via the NoC, communicate directly with DRAM, with external memory, again without PL involvement at all. So AI could initiate transactions, initiate read and write transactions on memory, and then take those and operate on them. What it could also do, although I don't know if I've shown that here, what it can also do is, if the data in DRAM needs to be reshaped in order for easy consumption by PL, by AI, it could stream that data through PL to AI. So you can use the APL just as a data shaper. So if the data is not in the right shape that you want to pad zeros, you want to reshape it, you want to have multiple copies of it, you can use PL for all of that. So this is an example of a 5G application now mapped to such a structure. Right? So a typical digital radio application has these functions: CIPRI, which is an interface functionality, DUC, DPD, and the ADC DAC functionality. Right? And all the signal processing heavy operations can now map onto AI engine. The interface functionality maps on the PL, and the ADC DAC are hardened blocks in our RF devices. So such a device now can do very, very high compute dense operations on just one device. Right? So that's how we scaled the device. Now let's talk about scaling the platform. Scaling compute and scaling interconnect directly inform the performance that the device is able to give. But we need to be able to scale the platform in order to make it so that this performance is extractable from the device. And given the markets that we are entering, given that we are talking to people who are software engineers, who are not hardware engineers, it is very, very important that we scale platform, and I'll motivate that in a little while. Right? So how did we scale the FPGA platform? One of the key things we did in FPGA was to make programming the FPGA and reading back the FPGA. By reading back, I mean FPGA provides you the capability to read every register in the FPGA. This is used by a lot of end applications. It's used by aerospace and defense applications because, space applications, because space applications want to guard against corruption because of cosmic rays, because of various single event events. And so it's important that we be able to read the state and confirm that the state is legal. And this functionality is key to that application. Secondly, FPGAs are used in emulation platforms. And in emulation platforms, you are essentially trying to debug your design by using FPGA as a simulator rather than to compute. And when you do that, you want to observe the various signals that make up your design. And so reading back state is very important. And so what we've been able to do this time is improve the read back capabilities tremendously. We are able to read back capability roughly 50 to 300 times faster than what we've been able to do in previous generation. In fact, what we are able to do for small devices, by small I don't mean large emulation class devices, but by small I mean a few million LUTs, like 1 or 2 million LUT devices. What we are able to do there is we are able to snapshot your design at a rate of 50 megahertz, independent of the device frequency. So at every 50 megahertz clock cycle, you can take a snapshot of your design. And you can do that while the design is continuing to progress. We've hardened a lot, and so this actually slide is showing that. So what we had was we had devices in previous generation that went into data centers. So for example, even right now in AWS, you can use our previous generation device to offload some compute or to do whatever your application desires. But in a data center setting, a large portion of the device is dedicated for platform functionality, because the data center has to manage this device, and ensuring the management of the device requires us to implement a lot of functionality in FPGA programmable logic. So a lot of the programmable logic gets used just for device management. In Versal, this entire thing vanishes. So the entire device now is available for your application. This is one of the key reasons why we had to put in the NoC, we had to put in hardened memory controller, we had to put in newer communication protocol, CPM, so that you don't need to have a soft logic in the PL just to be able to use it in a data center setting. And NoC has been part of helping Versal be a scalable platform. What NoC lets us do is to disaggregate communication and compute. The person who is interested in optimizing the compute doesn't need to worry about communication. And the person who is effecting the communication, global communication, doesn't need to worry about what compute happens on the other side. Right? So the user now specifies communication requirements at a very abstract level. The person designing the communication backbone on the FPGA only needs to know about the bandwidth requirements of every claimant of the memory bandwidth, for example. It doesn't need to know what it is doing there. Traditionally, this was a first-class concern because, as I said, you had to physically locate your memory and your compute close to each other. Now I can disaggregate them. You don't need to do any synthesis, place, and route in order to do a global data communication backbone now. Compute need not co-locate with data. Kernels who do the compute can be placed in locations that are convenient for them. They do not need to be placed in location where it is convenient for the global data memory, global data movement architecture. So I can now solve the kernel timing closure problem independently of the communication problem. In fact, there's no timing closure problem for communication because it's guaranteed correct by construction by NoC because we've hardened it. Right? So we don't have to worry about timing closure at the design level. We only have to worry about timing closure at the kernel level, which is a far simpler problem. That helps us scale the platform tremendously. Right? And the NoC architecture permits this. NoC architecture has distributed routing tables. There is no centralized orchestration of traffic. The connections are QoS managed. So if there is some data movement which needs to get priority over some other data movement, there are programmability hooks in the switches that lets you do QoS. You can dynamically reconfigure your NoC as well. And that's, for example, when you start your device, these could be the flows in your device. And as your device is running, you could bring in and bring out and remove some connectivity in your device as the device is running. So without interrupting the other flows, the NoC can be reprogrammed. What this lets you do is, when you are building up a device, during one stage of your operation, you might want some data flows. And during some other stage of operation, you might want some other data flows. But the traditional data flows need to continue. For example, the traditional data flows might be some infrastructure-related flows which you cannot interrupt. So you cannot simply say, let me pause everything, let me reprogram, and then let me do it. You're not able to, that is not a valid way of programming for that workload. The fact that you can dynamically reconfigure the NoC and still have some flows continue is a key feature. Right? There are several quality of service features that the NoC supports. So for example, you can say that this particular traffic is low latency. So if that traffic is low latency, it will get the highest priority among all. So for example, the processor requires very low latency communication with DDR. And in fact, in previous generations, we had to co-locate that DDR with the processor because of the low latency requirement. So what happened in previous generation was there was a memory which was co-located with the processor. Because the memory was co-located with the processor had very low latency access to the memory, but nobody else could have access to that memory in a reasonable way. Now, this memory has been disaggregated. So the memory is now accessible to everybody, but the processor can demand low latency access to them. So now you can do very interesting ways of orchestrating data movement. Some compute can deposit their results in this memory, and the processor now has access to this memory in a low latency way. So orchestrating between the processor and the PL, or orchestrating between processor and AIE now is much more efficient because of this traffic classes that we support. For example, isochronous traffic classes. There are a lot of applications, especially video streaming, which don't care about low latency. As long as you meet some latency requirement, they are fine. And so there is support which says that, this traffic absolutely needs to have a round trip latency of say 10 nanoseconds. And so the compiler and the switchbox will ensure that. And finally, there is a best effort where do the best you can. It's fine if you're not able to meet the bandwidth requirement given the topology, but give me as best as you can. So the NoC compiler now takes in user traffic specification, constraints, and gives you a global data movement architecture in minutes, not in hours, without touching the programmable level fabric. So this is an immense benefit when we are designing entire systems on an FPGA. Right? So let me end. This is my final slide. Reconfigurable computing is a key weapon we have in our attempt to deliver very high performance, domain specific compute. And in a world where technology is not giving you a lot of performance benefit, designing innovative reconfigurable architectures is a very productive vector along which performance can be improved. In fact, the latest AMD laptop processor now has dedicated Versal class, in fact, much better than Versal class AI engines hardened in them, because the CPU architects recognized the key benefits of a reconfigurable fabric, reconfigurable compute fabric within in a laptop setting. So I think this is a very interesting field, a field where there is a lot of innovation. So as graduate students, I really encourage you to take a hard look at what is possible in this space. Thank you.